Hello friends, this is Sumit and today we shall discuss an important topic, whether volume change takes place when a body elongates or compressed under the action of a load. Whether volume change takes place or not. So let us take a prismatic bar and let us elongate it by applying a load P in the axial direction. We see that there is an obvious increase in volume in the axial direction denoted by del V1. We have distributed it accordingly on either side because of the symmetry. So del V1 is the volume increase in the axial direction, and correspondingly due to the material property it contracts in the lateral directions. So let us suppose del V1 is the increase in volume due to elongation in axial direction, and del V2 is the decrease in volume which can be attributed to contraction in the lateral direction. Whether del V1 is equal to del V2 or not, that we have to see. Okay, it is sometimes mistaken by students that increase in volume due to elongation in the axial direction is equal to decrease in volume due to contraction in the lateral direction, and they think that del V1 is equal to del V2 and the net change in volume is 0, and just mistake this important natural phenomena by understanding it as a mere geometrical readjustment. Okay, so let us do a reality check and find out whether there is a tangible decrease in volume or increase in volume, or the volume remains constant when we elongate a material applying a load P. To start with, let us take some initial assumptions. So the first assumption that we'll take is that the bar that we are going to use in this discussion for our analysis is a prismatic bar. A prismatic bar is something that has a uniform cross-section area. The second assumption that we are going to take is the material that we are using in this bar is homogeneous and isotropic. By telling homogeneous, we mean that the composition is uniform throughout the bar. And isotropic, what does isotropic mean? At this point of time, I'll try to explain that isotropic means that in any point within the body, let us suppose at point A, if we take the properties in all the directions, all the properties should be equal. So let us take point A as our point of observation. So this is point A, and let us take one of the properties, say Young's modulus. So in the x direction, Young's modulus Ex. Y direction, let us take Young's modulus is Ey. In the z direction, Ez. In the nth direction, let us suppose it is En. So Young's modulus at point A in all the directions will be equal. So Ex will be equal to Ey, will be equal to Ez, will be equal to En. Okay. So these are the two assumptions. The third assumption that we'll take is that we will elongate the material such that it lies in the linear elastic region of the stress strain curve. In the last lecture, I had explained you as to up to the proportional limit, the body holds the linear and elastic nature, and Hooke's law can be applicable. So these are the three basic assumptions that we'll start with. The first three basic assumptions that we'll start with. So now we have a prismatic bar which has homogeneous and isotropic material, and it is elongated in the axial direction under the proportional limit. So now let us start analyzing and see whether there is a tangible change in volume or not. Okay, so for our discussion, we have taken this prismatic bar which has initial dimension as A, and when C through the lateral direction, this is the cross section which is B and C. So the initial dimensions of the prismatic bar that we have taken is A, B and C. So let us now load the material by applying load P in the axial direction and find out what is the change in the dimensions. Okay, so final length in x direction after elongation will be A plus delta A, isn't it? And now, as we know that delta A by A, that is change in length by original length, is strain, we can write delta A as strain into A. So this thing we can write as A plus epsilon A, which is equal to A into 1 plus epsilon. So this is the final length in the x direction. Let us now calculate what is the final length in the y direction. Okay, so final length in y direction can be written as b, because b minus del b. Here we come at an important point wherein we find difficult to calculate del b. What is the change in length in the lateral direction when change in length in axial direction is del a? Okay, so to calculate del b, we will discuss an important concept, a very important natural phenomena that every material exhibits. Okay, is the Poisson's ratio. So now what is Poisson's ratio? If we take a prismatic bar which is drawn in blue here and it is elongated or pulled along the axis applying a load P, the scientist Poisson, he was a French scientist, he found out that the strain in the lateral direction, that is change in dimension by original dimension in the lateral direction, is proportional to change in dimension by original dimension in the axial direction. So that we can write as the strain in the lateral direction he found out to be proportional to strain in the longitudinal direction, and when multiplied by a constant it becomes equality holds. So this constant is called the Poisson's ratio and is denoted by nu. So now we know that the Poisson's ratio is equal to lateral strain divided by longitudinal strain. Okay, we are multiplying it by a minus sign because lateral strain in many materials of engineering use is having a negative sign. That is, see here it's a negative sign, it is elongating, this compressing. So to take care of that, we put this minus sign here. Okay, so now since we have understood Poisson's ratio, we'll see that what is our target. Target is to calculate del b, how much change in length in the axial direction has happened. To calculate this, actually, since we have understood what is Poisson's ratio, so we'll write here Poisson's ratio is equal to minus strain in the lateral direction divided by strain in the axial direction or longitudinal direction. Okay, so this is our Poisson's ratio. Now here if we see what is our initial length in the lateral direction, b. Okay, and initial length in the axial direction is a. So strain in the lateral direction will be del b by b and strain in axial direction will be del a by a. Since we already know that this is taken as strain, here we have already assumed this as epsilon, so we can write minus del b upon b as nu into epsilon, or del b is equal to minus nu epsilon into b. So now we are able to calculate as to what change in the lateral dimension takes place when the material elongates in the axial direction, giving us strain epsilon. Okay, so we'll substitute this in this equation. Okay, and we'll find out what happens. So putting the value of del b here, we find out that final dimension y direction will be b minus nu epsilon into b, which is equal to b into 1 minus nu epsilon. Okay, so this is the final dimension, the y direction. Now similarly, by applying the concept of Poisson's ratio, we can calculate the final length in z direction also. In z direction will be equal to c minus del c, isn't it? And del c, if we can calculate by using Poisson's ratio, so it will be written as c into 1 minus nu epsilon. Here nu is taken same in y and z direction because we have considered a isotropic material. Now since we have got the final length in all the three dimensions, that is in x direction, y direction, z direction, we can be able to calculate the final volume, because the volume of a cuboid is the product of length of the sides. Okay, so final volume will be A into 1 plus epsilon into B into 1 minus nu epsilon into C into 1 minus nu epsilon. So this is our final volume. Let us do some calculation. So ABC and 1 plus epsilon will come in 1 minus nu epsilon square. So we'll take a separate page and we'll do some calculations in order to find out this thing. Okay, so final volume VF is ABC 1 plus epsilon. I'll go step by step, there's no hurry. Nu square epsilon square minus 2 nu epsilon, isn't it? Now see, epsilon is a very small quantity. Strain, we are restricting it to very small value. So square of epsilon will obviously be very small. So we can neglect this. So ABC into 1 plus epsilon into 1 minus 2 nu epsilon. Okay. So ABC into 1 minus 2 nu epsilon plus epsilon minus 2 nu epsilon square. Now again we find that epsilon is a very small quantity and square of epsilon can obviously be neglected. So we'll neglect this and find the final volume as ABC into 1 minus 1 plus epsilon minus 2 nu epsilon. So this is our final volume calculated. Okay, we'll write this thing here. So our final volume is ABC into 1 plus epsilon minus 2 nu epsilon. Okay. Now since we already know what is our initial volume, so what is our initial volume? Initial volume of a cuboid, product of side of lengths of sides. So it will be ABC. So change in volume we can calculate by subtracting initial volume from final volume, which can be written as ABC 1 plus epsilon minus 2 nu epsilon minus ABC. We'll take another page. We'll continue after this. Okay. So here we see that change in volume is equal to ABC, and we'll put this in bracket. So 1 plus epsilon minus 2 nu epsilon minus 1. So 1 and 1 can be cancelled here. So we'll take ABC epsilon minus 2 nu epsilon. We can take epsilon also out now. See, we're going step by step to avoid any confusion at a later stage. So 1 minus 2 nu. ABC, as we know, it is the initial volume. So we can write V naught into epsilon into 1 minus 2 nu. And epsilon, since we have, we are in the linear elastic region. We have elongated the material such that it lies within the linear elastic region. So Hooke's law can be applied. Hooke's law can be applied. So by applying Hooke's law, we get stress is equal to Young's modulus into strain. And our strain accordingly will be sigma by E. Isn't it? So we'll substitute sigma here. So it becomes initial volume into sigma by E into 1 minus 2 nu, isn't it? So since we have calculated the change in volume, this is the change in volume. When we assume that the initial dimensions or initial volume is V naught. So we let us understand one more term here, that is called dilation. Dilation actually means the change in volume per unit volume. Okay, so our dilation, which is denoted by E, will divided by V naught, so it becomes sigma by E 1 minus 2 nu. Okay. So this is the dilation. So now we are in a condition to say whether there is a change in volume taking place as a result of elongation by applying a load P. So this is the change in volume, per unit volume. This is the dilation that is caused by the elongating the material. Okay. Now let us take few examples to properly understand as to what this change in volume means. Okay. Here we have already seen that change in volume is a function of Poisson's ratio. Change in volume is a function of Poisson's ratio. So, see, if suppose we have Poisson's ratio value as 0.5, then what will be the change in volume? There will be no change in volume. Okay. But if Poisson's ratio value is 0, okay, so there will be a definite change in volume. So we'll take few examples to understand this phenomena. Okay. One by one we'll go. So here, after finding out this expression, we can conclude, or we can conclusively say with evidence, that elongation and associated contraction, which can be attributed to Poisson's ratio, is not merely a geometrical readjustment in which same volume is retained, but tangible volume change takes place. Okay. This will be demonstrating with the help of examples. So we'll first take rubber. Our first example is rubber, and second example is cork. So for rubber, actually Poisson's ratio is 0.5 and cork Poisson's ratio is 0. So let us take both these situations one by one. For rubber, where Poisson's ratio is 0.5 and we have already calculated dilation, that is change in volume per unit volume. Dilation formula we know, that is sigma by E 1 minus 2 nu. Let us put 0.5 here. So our dilation will become 0. This means that in case of rubber, there is no change in volume. But this is a special case. And mere geometrical readjustment take place, retaining volume as constant. Okay. So in a special case of rubber, we find that since the Poisson's ratio is 0.5, there will be no change in volume taking place, and which is a special case actually. In other cases, we'll see that a constant or tangible volume change takes place. And here in case of rubber, it's a mere geometrical readjustment taking place. Okay, so here with the help of this diagram, we'll try to understand that the initial, we'll take a prismatic bar and we'll elongate it along the axial direction applying a load P. So the initial dimension was A, B and C in the X, Y and Z direction, and initial volume will be product of the side length, that is ABC. Now what will be the final volume here? So as we elongate it, the final dimension, the X direction final length becomes X, in Y direction is Y and Z direction is Z. So final volume will be X, Y, Z. So here in case of rubber, as we have studied, there is no tangible change in volume, and only this dimension geometrical readjustment takes place, retaining the same value. Here ABC will be equal to X, Y, Z. So this is a special case where Poisson's ratio is 0.5. we'll take a second case of a cork, okay, wherein Poisson's ratio is 0. So let us put in the dilation formula E is equal to sigma by E 1 minus 2 nu, which is equal to sigma by E into 1, because nu becomes 0. This means that change in volume per unit volume is equal to only strain, okay, and this can be written as strain, which is del A by A. This is dilation. When we calculate the total volume change, it will be multiplied by initial volume. So when multiplying by initial volume, we'll get del A by A into ABC. Okay, here is the cork prismatic bar that we have taken, having initial dimension A, B and C. So we'll multiply by A, B and C, and by cancelling this we find that the final change in volume is del A into BC. What is BC? BC is the cross sectional area and change in length is del A. So in case of cork we see that as we elongate the material by applying a load P, the lateral dimensions do not change. Lateral dimensions do not change, and there is only a change in the longitudinal direction. Okay, that is del A, because of which the change in volume is del A into area of cross section, which is del A, that is change in length in x direction into area of cross section. Okay, so this is the change in volume in case of cork. So these are two special cases. In the first special case, that is of rubber, we saw that there is no volume change occurring, and the change in dimensions is actually a mere adjustment, a geometrical readjustment taking place. But in case of cork, we saw that as we elongate the material, it will only elongate in the axial direction and no parallel contraction is seen in the lateral direction, because of which the change in volume is area of cross section into change in length in the x direction. So these are two special cases. We'll discuss two more. Let us start one by one. So now we'll see mild steel. Okay, let us take mild steel as another example. So here we see, we'll take a prismatic bar in which the initial dimensions are A, B and C. So as we have discussed here, see, there will be some tangible change in volume and lengths also. See, A becomes A plus A into 1 plus epsilon, B becomes B into 1 minus epsilon into Poisson's ratio, C becomes C into 1 minus epsilon into Poisson's ratio. So here we see that there is a tangible change in length. See, A becomes A into 1 plus epsilon, as we have already discussed it earlier. B becomes B into 1 minus nu epsilon, and C becomes C into 1 minus nu epsilon. And the change in volume, it will be, as we have already calculated it, that it will be sigma by E into 1 minus 2 into Poisson's ratio into initial volume. Okay, so this is the change in volume. So here we see in case of mild steel, wherein we have Poisson's ratio as 0.3, we see that when elongation takes place, contraction is also happening parallelly, and the net change in volume is a tangible value. Okay, so we'll come back to our initial question that we were to study about, is that whether volume change take place when a body elongates or compresses under the action of a load. So I thought that the students have a general confusion that the increase in volume in the axial direction is taken care by the decrease in volume in the lateral direction, and net change in volume is 0. So here it is proven that net change in volume is not 0. It is 0 only when the Poisson's ratio value is 0.5, which is true in case of rubber. In other cases, there is a tangible change in volume seen. Now let us take a separate example. See, before starting auxetics, I will just let you know about the range in which Poisson's ratio lie. See, Poisson's ratio range lies between For most of the materials in general engineering use, Poisson's ratio lies between 0 and 0.5. Okay, but the practical value of Poisson's ratio is actually between 0.5 and -1. Okay, Poisson's ratio lies between -1 and 0.5, but for general materials we find that it lies between 0 and 0.5. General materials of engineering use. Here we will discuss about an important class of materials called auxetics, for which Poisson's ratio value is negative. Ratio is negative. So what does this negative value of Poisson's ratio mean? It means that when we apply a load P elongating a body in the axial direction, normally what is seen, see we have seen here, normally what is seen is there a decrease in cross-sectional area, isn't it? So, but in case of auxetics, where we have negative Poisson's ratio, we see that as after applying load in the axial direction, as it is elongating in the axial direction, the lateral direction also it will elongate. Okay, here we see that initial length was A, so obviously it has increased to A into 1 plus epsilon. Okay, but parallelly we see that there's a general understanding that when we elongate a thing, it should contract in the lateral direction. But in case of auxetics, since the Poisson's ratio is negative, we see that there is increase in lateral directions also. Sorry. See here, dimension C becomes C into 1 plus nu epsilon. Okay. So this is a special case of material in which as while elongation means in addition to the lateral elongation, it elongates in the in addition to the axial elongation, it elongates in the lateral direction also. So this is a special case. So here we have seen four examples, isn't it? First was that of a rubber, in which no volume change takes place because Poisson's ratio was 0.5. Second was that of cork, in which volume change takes place due to elongation only in the axial direction and is not accompanied by contraction in the lateral direction. Third example that we saw is of a mild steel, wherein dimension changes takes place in all the three directions, giving a tangible value for the change in volume. And fourth example, that is a special case of auxetics, wherein Poisson's ratio is negative, that we have discussed, that in addition to elongation in the axial direction, instead of being contracting in the lateral direction, it is elongated in the lateral direction also. So now, as we have started a reality check whether the change in volume due to increase in length and decrease in volume due to contraction in cross-sectional area because of loading in the axial direction, does it yield zero volume change? So here we conclude that no, this assumption is wrong. There is a definite volume change occurring unless the Poisson's ratio value is 0.5 in the material when it is elongated or compressed by applying an external load P. This is all that I have to discuss about this important phenomena. So if you have any queries, you can please write to me. And if you have liked this video, please click on the like button, comment and subscribe. Thank you.